The central question explored in this framework is whether angular momentum must be realized exclusively within matter fields, or whether geometry itself may contribute to the effective angular momentum budget. This possibility is considered within a geometric framework in which geometry is treated as an active participant rather than a passive background. More broadly, the framework is built upon the idea that time is not a carrier of change, but an index of change. Persistence is therefore not realized through time itself, but through geometry. Geometry acts as the carrier structure, while the connection provides the relational and transport structure through which physical relations are realized. Within the present work, this orientation is formalized using a Riemann Cartan-Type spatial manifold equipped with a Poincaré gauge connection, interpreted within a non-minimal Einstein-Cartan extension in which torsion remains dynamical, providing a second geometric degree of freedom alongside curvature. A further distinction is made between the torsion and contortion sectors. Torsion supplies an additional geometric degree of freedom alongside curvature, while the contortion sector encodes how torsion modifies the connection. In this sense, torsion belongs to the geometric structure itself, whereas contortion links that geometric structure to the relational and transport structure defined by the connection without introducing an additional independent degree of freedom. The cosmological setting adopted throughout is a Buchert-averaged timescape model, providing the effective large-scale description within which the consequences of the underlying Riemann Cartan-Type manifold, equipped with a Poincaré gauge connection that defines its associated geometry, are explored. The motivation for considering geometric contributions arises from broader questions concerning the accounting and decomposition of angular momentum. Although total angular momentum is conserved, the identification and partitioning of its constituent contributions remain active areas of research. The proton spin problem is invoked here as one example of such questions rather than as a problem the framework seeks to solve. Its significance for the present discussion is not that it demonstrates a geometric contribution to angular momentum, but that it illustrates how questions concerning angular momentum accounting can remain open even when the total quantity itself is conserved. In this sense, it motivates asking whether existing decompositions necessarily exhaust all physically meaningful contributions. Importantly, the present framework does not propose a geometric contribution within nucleon structure, nor does it attempt to bridge directly between proton-scale physics and cosmological structure. Instead, it asks the analogous question at the level of effective large-scale geometry. If geometry possesses independent dynamical degrees of freedom, might part of the angular momentum distribution be realized geometrically rather than exclusively within matter fields? We refer to this candidate contribution as geometric angular momentum. In the present framework, this contribution is sought not at the scale of strong interaction physics, but within the effective geometric description of large-scale cosmic structure. The dynamical torsion sector therefore provides a candidate mechanism through which such a contribution might be realized. Within the Buchert-averaged timescape framework, the proposal is that torsion may contribute to the effective angular momentum budget through its influence on domain-scale geometry. In that context, geometric angular momentum would be expected to manifest not through proton structure, but through vorticity, rotation, and their contribution to kinematic back reaction across cosmological domains. The broader significance extends beyond angular momentum alone. Once geometry is treated as an active participant rather than a passive background, questions of persistence, transport, organization, and effective physical structure also become geometric questions. Geometric angular momentum is therefore presented as one consequence of a more general shift toward geometry as the primary carrier structure within the framework. From this perspective, the framework begins to resemble spatial geometry more than space-time. Time does not contain persistence, carry evolution, or act as a state-bearing medium. It simply indexes the ordering of configurations. The manifold and connection, together with the curvature, torsion, and contortion sectors, therefore become participants in the geometric structure through which persistence, transport, and physical relations are realized. This is why the framework increasingly points toward a Riemann Cartan-Type spatial manifold equipped with a Poincaré gauge connection, rather than a purely metric geometry in which curvature alone exhausts the available geometric degrees of freedom. The framework presented here should therefore be understood as a developing geometric proposal rather than a completed formal theory. The central orientation, the geometric role assigned to curvature and dynamical torsion, and the cosmological setting provide the present foundation. At the same time, aspects of the formalism, including the precise character of the underlying manifold and the associated geometric update operator, remain open to further development and refinement. The designation Riemann Cartan-Type reflects this continuing work while indicating the geometric direction in which the framework is evolving.